Second to last Friday, right? Homework is due today. Quiz, you haven't. I mean, you had the option. There's no way you got it done, okay? But it is open now, and it's open now until the end of Sunday. Okay, that is quiz number 9. We will have quiz number 10 and homework number 10. I will assign that probably this weekend. Not exactly sure when it's going to be due. What would you rather have? Okay, I'll open this up. We'll make it democratic here. Okay, we will have a quiz and a homework. We have an exam on Wednesday. Would you want the homework due on Monday and the quiz due up until our final, like the day of the final? Or would you rather have the homework due, say, Friday, and then same thing, quiz is due by Sunday, the weekend before our finals?
How valuable is having the solutions to that homework to our final?
It's going to be valuable. It's going to be over pressure vessels and combined loading, which essentially is just everything that we've talked about so far in this class.
Might as well just keep it the same.
Yeah, I would
Same?
keep it.
I would
Okay.
have to say.
Okay, same it is. See, look at that. Give a little, kind of, sort of. Quiz drop? What? Did you hear that? No, but I have teacher evaluations. Okay, they used to go around with an envelope, which made sure that everyone would fill the damn thing out. Now it's online, so to incentivize you guys to talk shit about me, I would like to offer an opportunity, okay? If we get 75% of the class to go out there and fill this out, okay? And I'll put a link on D2L so you guys can go out and find it, okay? Maybe you guys already know where those are. Maybe you've already gotten emails. I think they're already available. But if we get 75%, I'll add 3 extra credit points to the final, okay? That's 3% to the final. Seem fair? Okay, so go out there and no quiz.
On that announcement, will you please put?
Yeah, Jesus.
Will you please put extra credit as the first thing that they read on that announcement? So
Yes,
get the
okay.
Less than
75%.
75%.
Extra
Don't
credit
start
off.
it off with extra quiz or like please fill this
Yeah.
out.
Okay, all right, deal.
4 extra credit.
Yeah, extra
3%. So that's not the same as dropping a quiz by any means, but it is something, okay? And it's to my benefit. So I would honestly, I mean, I'm joking when I say talk shit, but if you do not like how I've done this, tell me why. And I will listen. I'm going to try and listen. Maybe I'll read them, maybe I'll burn them, I don't know. I guess I can't really burn it, it's on the computer.
Print them out just to burn them.
Yeah, exactly. Exactly. Okay. Anything else? I think that pretty much wraps up everything that we have, which is really not much. We've got 3 more classes to meet next week, and then 1 more 110 minutes me versus you sort of experience. Okay. That's it? Okay. It's kind of what it is, me versus you. So, the last part of this class is chapter 15, which is combined loading. And we actually went over a little bit of chapter 15 earlier on when we were talking about axial and torsion. Okay? But I bring this picture up just to show you that the real world is a lot more complicated than that, right? We've got a lot of things going on. We don't not only have axial load and torsional loads, but we've got bending loads. We've got pressure loads potentially, okay? The crane, all right? I love cranes, okay? All right? They're amazing pieces of machinery, okay? So in this case, we got this big crane boom, right? Well, it's under flexure and axial load, right? We've got outriggers that have 3,000 PSI hydraulic pressure in the rams, right? So we can jack these things up and make them level, right? Those rams not only have the pressure acting on them, right? We have hoop stresses. They're cylindrical pressure vessels. Hoop stresses, but we also have axial forces acting on them as well, right? Also, city street, right? We have street lights, okay? The weight of the street lights hanging on them is bending the street light itself, right? Which induces bending down here at the base and throughout the entire length. Also creates axial load down here at the base where it hits the sidewalk. And then I don't know if you guys have ever seen, I had a picture and I tried finding it, I could not find it, of a Couldn't find it. Here's another one, but of a dump truck going down 19th, and the dump truck bed came up and it grabbed one of the light poles, okay? Swung it around. Well, that light pole now had bending, axial load, and torsion, right? Unfortunately, not enough capacity. Dump truck just took that thing right out, right? But in a windstorm, you guys have probably seen them swaying, right? Well, those are deflections. We'd have to have allowable deflections. We would want that thing to move like 5 or 6 feet, right? So all of those things come together and culminate in engineering design, right? So that's what chapter 15 is about, is essentially taking all the pieces of this class, putting it all together so that you guys, when you're standing out in the real world, looking at maybe something like this or downtown, right? Buildings, signs, vehicles, all of those things. There's tons of different load sources. And hopefully after this class, you have 95% of the tools to analyze pretty much everything, which is really cool, right? You can figure out what stresses are in things, knowing what material properties are. You guys can figure out what things can and can't handle, right? When is it gonna break, right? As civils, we rely heavily on the idea that we deal with big shit, like really expensive stuff, okay? Like this building, for instance. You're not gonna build a building and then test it to make sure it's safe enough for people to be in it, right? Mechanicals have the advantage. I had a friend that worked for Lexmark, right? If they wanted to change a component in a printer, they just go manufacture a new component and try it out, right? Costs a few dollars, a few hours of people's time. Well, in a building, you can't really prototype like that, okay? So that's where design becomes very, very critical, okay? So that's why I love this class, okay? I love engineering. It's just cool shit. All right. So, last part of this class is combined loading. I call this combined loading part 2. As I mentioned, this is chapter 15 in the text. Okay. Also, as I mentioned, the real world is not simple. Right? All those little trusses or individual cylindrical tubes or pipes, that we had cantilevered off a wall with one single load on them, right? That the simplicity of a lot of the problems that we've been dealing with up till now doesn't happen as often, right? We've got a lot of combined loading that happens in the real world. Our initial combined loading exercises, I had a couple examples of a propeller, right? Which the shaft would be induced with axial and torsion, axial thrusting the vessel forward, and then torsion driving the shaft itself. That's for the METs, and for you CETs, right? Drill rig. This was up in Spanish Peaks. Talked about that, which I was up there recently. Massive, massive building. Huge cranes. Like, go drive up there. Seriously, if you're in Big Sky. It's all public, open to the public. All the roads are. Okay? They have really good mountain biking trails, I guess, in the summer. They're all public too. Check it out. Roller coasters. Well, we got all types of shit going on, right? Bending, torsion, axial. Talked about our street light, right? We've got the axial weight. The weight of all that stuff hanging out there has to come back. It's going to be an axial load that acts on the column or post. We've got a moment that would be acting at the top of our post due to the cantilevered member out there carrying all of the street lights. And then, as we mentioned, in the wind or unrealistic scenarios like a dump truck running into it, right, we would have some torsional demands as well. So we have, axial plus torsion plus bending. All right, this is our axial loads, torsion, and bending. We can have bending in multiple, one or two axis bending, right? We can have forces acting in two directions on the end of something. I keep going to... And we can also have pressure. Right? I mean, you can't really see it, but these are all radiators, right? If you go to Roberts Hall, basement of Roberts Hall, basement of this building, right? We've got to transport all of this high pressure steam around the entire campus. So that pipework has to carry its own self-weight, right? So it's snaking its way through all the buildings, through all the utilidors that run underground between all the buildings on campus. So we've got, at times, we've got axial bending and pressure or torsion, right? All of those load sources that potentially act at once, okay? So if we look at these force origins, axial, torsion, bending, pressure, right? We have some analysis methods, okay? We usually divide them into two groups. One is if we're dealing with beams, because they're kind of special and out by themselves. Okay, if we're dealing with just strictly beams, we would start by doing a free body diagram, right? We do that with any sort of engineering analysis when we're talking about deriving forces, right, and stresses. So we do a free body diagram. We do this because we want to find reactions. Once we have a free body diagram established, we know what our reactions are, well then we can figure out what our loading diagrams are, or more specifically, right, our internal shear and moments. Once we know what our internal forces are, our shear and moments are in our beam, we can then jump to figuring out what our stress block looks like, right? We're going to calculate, in order to figure that out, we're going to calculate stresses. Oops. Stresses on our block based on our loads and geometry. So we figure out our loading diagram, shear and moment, right? For shear stresses, VQ over IT or IB. Moments, MY over I, right? Or M over S. We can figure out what our stresses are. Then we know that our moments induce normal stresses, right? Our shears induce shear stresses, so we can figure out our little block and apply our shear stresses and our moments onto our little block. Once we have that, then we can jump to Moore's circle. And here we determine those principal stresses. And stresses at a plane of interest. Right? Maybe there's a weld at a certain angle, connection, and we can figure out what those stresses are applied at a specific location, at a specific orientation. Principal stresses, we use those because those are our maximum stresses, right? Sigma 1 and sigma 2, the far right and the far left of our Moore's circle, right? Those are our extreme stresses, and that's what we would relate to, say, an allowable stress, which would be, say, the failure stress of a material divided by a factor of safety, what we're allowing the material to go to. Okay. In beams might have axial loads also, right? But same sort of derivation. We figure out what our reactions are, right? We could have an axial load in our beam. If we have an axial load, we would calculate stresses based on force over an area, normal stresses. We've done that already. We can figure out our stresses on a stress block, and then we would determine our Moore's circle, and we could figure out the stresses at any orientation. Right? So that's beams. If we look at other members, I'd say more involved members that have a lot more going on. Again, we would start with our free body diagram. And I say 2 times. Well, what we do is we break our element into 2 force systems. And this will make sense when we go through the example. But we're going to start looking at forces and moments. And this is really just a housekeeping exercise in order to keep all of the stresses organized and forces organized. So there's no confusion. We don't add something when we're not supposed to, or subtract something when we're not supposed to, or supposed to. Okay? Essentially, if you had right, well, let's just go to it. This is going to be an example that we go through. Right? We had a pipe hanging off of a wall, right? And it had these 2 forces applied to it. And if we looked at the stresses here at the wall, well, the vertical force is going to be trying to bend or cantilever this pipe off the wall, right? And this force is going to want to twist this pipe at the wall as well as bend it at the wall, right? And if this pipe had, say, an axial load on it, right? Those bending stresses and axial loads are going to be acting in the same direction. So you essentially have superposition going on, right? This one force is going to create stresses that might add to this force's stresses as well. Okay? So we, in order to keep the housekeeping organized, we essentially determine, well, what are the forces and the moments applied due to these applied forces at the point of interest, and then we separate them, and we're going to look at what are those forces acting at, say, this section, and what are the moments acting at this section. We'll run through and figure out what the stresses are that those forces and moments create, and then we go back at the very end, we're going to add them together. Okay? So we do a free body diagram. We essentially do it twice. We figure out what these force systems are, what are the forces and moments, which means we have 2 sketches. One with force, one with moment. Okay. From there, in each of those 2 stresses, right? Those free body diagrams, we're going to have forces which create stresses, and we're going to have moments that create stresses. And so we're going to develop our stress blocks. Whoops. And we do that. We determine all stresses due to forces and moments. Pressure too. I'm trying to make sure we don't forget pressure because it can be there. Oops. Whoa. Present. Come on. Gotta slow down. Okay. So based on those forces and moments, if it's an axial force, right, we're gonna have axial stress. Axial stress is in the axis of our member, right? Well, if we have bending in that member, we're also gonna have bending stresses that are in the same direction. right? So we're going to develop what are the stresses due to the forces, what are the stresses due to the moments, and then we can add them together on a single stress block, okay? This is where we get into superposition, right? So we're going to add stresses at point of interest to determine the complete stress state. In other words, we're going to develop the complete stress block. Right? And then finally, as with our beams procedure, we are going to develop Moore's circle so we can figure out our principal stresses. Or stress on a plane. Right, of interest. It's going to be due to some connection or some material change, something that's happening at a specific orientation in our member, right? Big thing here is we as designers and engineers, right? We also get to pick where we want to know what the stresses are. Right? We always say in these procedures, right? We are figuring out, calculate stresses on a block based on the loads and geometry, or break into two force systems, determine all stresses due to forces and moments. Well, these stresses that we determine are at a location of interest, right? And in all these homework problems, the quiz problems, all of that, I've given that to you. Well, in the real world, that's where you have to look at something and determine, where am I going to analyze this? Where do I think the maximum stresses are? What are critical locations along my member or element that I'm designing? Right? So that's on us as designers to do that. And then we can figure out, well, what's the maximum at those locations, right? But picking one location does not mean it's the maximum throughout the entire beam. Right? So in this example, we're going to look at a beam element. It's got a couple different load sources. It's got a uniform load, right? Constant magnitude over partial length, right? Half the length. And then we got a point load that's sitting at a quarter point from the right end. And they're asking us for what is the stress state at points H and K, right? And H and K, more specifically, are at certain locations along the cross section. So we have the longitudinal location of our points, right? H and K. H is 1 meter from the left end. K is 4 meters from the left end. Okay? And then on top of that, H is 35 millimeters from the center line, right, or the centroid of our eye shape, and K is 75 millimeters above the centroid of our eye shape. But as you guys will learn when you get into actual practice, right, figuring out H and K and where those are is up to us. We have to decide that, okay? Or we get a computer program that just looks at the entire beam all at once, right? Seems like the easiest approach. That's what I do. Right? But to have an understanding of it is critical. So in this case, we're going to look at a beam. We're going to look at 2 points, H and K. We're going to look at those H and K being H, as I mentioned, 35 millimeters down from the centroid, and K being 75 millimeters up. Well, if we go back to our procedure or analysis method here for beams, we're going to do a free body diagram. We're going to figure out our load diagrams, right? We want our internal forces. Notably, we want our internal forces at our points of interest, right? From that, we can figure out our stresses, right? And we can put those stresses on a stress block oriented with respect to our points of interest. And then finally, we could figure out what the principal stresses are, what the maximum shear stresses are, what the stresses are. If we had in this beam, we decided that we had a beam that was 5 meters long and 1 meter long, and we decided to weld the thing together at H. And even more so, we had two members that were at a 45-degree angle. We decided to weld them at a 45-degree angle, right? So we could use Moore's circle once we know what the stress state is at H, right? Our stress block is at H. We could devise a Moore's circle for that at H. Knowing the orientation of that weld line, we could figure out what are the stresses in the weld. And we could size what the weld needs to be, right? Are you using 70-18 rod or are you using 70-16 rod, right? What are you using? 60-14 rod? What are you gonna use, right? So, if we work our way through this and we start at step 1. Step 1 is our free body diagram. Well, I'm going to piggyback on this sketch and say this is my free body diagram. I don't want to draw this out, okay? Coordinates. Always have to have coordinates for a free body diagram. I have to indicate our external applied forces. We also have to indicate our reactions. In this case, at A and B, as we have mentioned before, we have what we would call pinned connections. And we have 3 equations of equilibrium, right? Well, we're gonna call this a roller. B is a roller, A is a pin, okay? 3 equations of equilibrium, 3 unknowns. This is a determinant system. We've got some of the forces in the X, some of the forces in the Y, and some of the moments. That gives us AX equal to 0, right? If we sum forces in the X, there's only one force in the X direction. No externally applied forces, so we get 0. AY, well, if we do some of the forces in the Y and some of the moments, we're going to get that AY is 195 kilonewtons and BY is 105 kilonewtons. Right? Which intuitively would make sense to me, stepping back after this. AY, there's more force applied on the left-hand side of the beam than there is on the right-hand side of the beam. Right? And so AY should be greater than BY, okay? Now we can jump to step 2. Step 2 was our internal forces, or our force diagrams, right? Loading diagrams, our shear and our moment diagrams. You guys have had quite a bit of practice with these by now. We looked at our shear diagram and we drew a moment diagram. Okay. Shear diagram is dependent on externally applied forces, right? So if we start on the left-hand side of the beam, we know AY is 195 kilonewtons. Acting upward, right? Nice. Is that one of those little like electric scooters?
No, it was just a motor bicycle.
Or sorry. That's just a bicycle?
Yeah, it was just a bicycle with,
Yeah.
Little one of those little.
little 20.
Really? Like
Yeah.
a little,
It looks more
like a weed eater motor?
Yeah, exactly.
Nice. So we got 195 kilonewtons, right? That changes our shear diagram. We jump upward to 195 kilonewtons. I'm going to move this dot over to here. Thank you. shear diagram changes with respect to externally applied loads, right? So if our uniform load is constant, then our change in our shear diagram is linear, right? And it's going to be linear until that load stops, right? Which is the center line of our beam. And it's going to change at a rate, right? The slope of our shear diagram is the magnitude of our externally applied load, right? That's why at a point load, it's a vertical jump. At a constant uniform load, it's linear. So if it's linear, we're going to go from there to here at a rate of negative 80 kilonewtons per meter. We're moving 3 meters, so we're going down 245. Or we're going, what? Yeah, 240 kilonewtons, right? So 195 minus 240 kilonewtons is negative 45 kilonewtons. Then we move from the center line of our beam over to the applied point load, 1.5 meters. We have no externally applied forces. So our shear diagram is going to stay the exact same. We're going to just sit right here at negative 45 kilonewtons. We're going to have a straight line, acts between them. Then at 4.5 meters from the left-hand side, we got this 60 kilonewton point load. That's going to further jump our, I'm going to get rid of that because that's in the way. Further jump our shear down by 60 kilonewtons. Well, 45 plus 60 is 105. We're going to have a constant 105 until we get to our reaction at the end, which is going to bring us right back to 0, which is what we always like to see. Okay. So that's our shear diagram. The moment, area under the shear curve. Well, our maximum is going to be where we hit 0. It's going to be right there. We're going to be gaining something like this. A lot at first, right? Because we're gaining based on the magnitude. The slope of our moment diagram is the magnitude of our shear diagram. Just like the slope of our shear diagram was the magnitude of the loading diagram. So it's going to increase sharper at the beginning and then taper off to 0 when the magnitude of shear is 0. If you do the area of that, we're going to get 238 kilonewton meters. Then it's going to start decreasing, right? Because we've got negative area now, where it's going to be decreasing. Well, if it's linear, then the moment diagram is nonlinear. It's going to start out decreasing slowly, and as the magnitude increases, it's going to decrease faster. We're going to get to another point. This point is going to be 225 kilonewton meters. Then when we have a constant shear, well, if our shear is constant, that means our moment diagram is linear, right? And the slope of that linear diagram is the magnitude of our shear diagram, or 45. So we're going to decrease at 45 kilonewtons per foot. And then finally, wow, this is really not to scale. We're going to decrease the rest of the way. We're going to go to 0. This is 157.5. Right? I don't know why I squished that like I did, but I did it. So we start at 0. We gain non-linearly because our shear diagram is linear. We lose some non-linearly because our shear diagram is linear. Now our shear diagram is constant, so we're going to decrease at a linear rate, right? First at 45, then at 105, and we're back down to 0 because we have a pin-pin beam condition, okay? So that's step 2, right? So now we have internal forces. Well, I guess not quite done yet, right? We have points H and K. That's our points of interest. So we really want to know what our internal forces are at those 2 points. So if we drew a line right here and a line right here. Okay. We're going to have a corresponding shear and moment at those points. Well, our shear is going to be 115 kilonewtons, and our moment is 155 kilonewton meters. Shear at point K is going to be negative 45, right? We're on that constant region of our shear diagram. And then if we ran the math and figured out what our moment was going to be, it's going to be 180 kilonewton meters at our point K. So if we go back and we look at a free body diagram of our points of interest, right? If we cut our beam at H and K, this would be part, just call this part 3. This is point H. If we do a free body diagram at point H, right? Those are our internal forces, right? Our shear is 115 kilonewtons. We know that it's a positive shear, up on the left, down on the right, so this is a positive shear. And we have a positive moment, 155 kilonewton meters. We have our reaction at A, AY is 195, and then we have our applied load. Right. At this point, at H, right, we've got this very small little square. This is our stress block. Well, at H, we've got not only a moment, but a shear, and we know that our moments give us normal stress, my over I, whoops, not what I wanted, tau is our VQ over I T. Our unknowns here, M, Y, I, V, Q, T, right? Out of all of these 6 variables, we now have moment and shear, right? So we need to figure out the rest of them. What is I, what is Y, or I, Y, Q, and T. Similarly, we're going to have to do the same exercise at point K. We got this free body diagram. And again, negative my over I, tau, VQ over IT. This is all similar exercises you guys have already done. Right? If we look at point H, point K. Point H, as I mentioned, was 35 millimeters down from the centroid of our I shape. So our Y, in this case, right? Y in our bending diagram, or our bending stress equation, right? And negative my over I. Y is the distance from the centroid to the point of interest. Positive upward. So if it's positive upward, we're below the centroid, so we have negative 35 millimeters, right? If we look at Y for, did I even write it in? Yeah. Y for point K, well, we are 75 millimeters above the neutral axis. We have a positive 75 millimeters. We also need to know what is our moment of inertia, IZ. Well, I am going to break this thing up, right? We could do moment of inertia of our top flange, moment of inertia of the bottom flange, and moment of inertia of the web, right? Knowing that the web, because the center of the web is coincident with the centroid of the total section, you don't have to worry about the parallel axis theorem. With the flanges though, the centroid of each of these flanges is a distance away from the centroid of the total section, right? So we would need to figure out the moment of inertia of our top flange and add to it the area times the distance of the centroid of that flange to the centroid of the full section squared, okay? And we'd essentially double that because we have a symmetric flange on the other side. So we could go about it that way. How I'm gonna go about it is I'm gonna take try and find a decent color here. I'm going to take the moment of inertia of the full section and then subtract out these two little rectangles. And the reason why I do that is we know that the moment of inertia of a rectangle is BH cubed over 12, right? Well, the centroid of this rectangle is the same as these rectangles, right, with respect to being right along this axis. This is the axis that we're trying to get our moment of inertia about. So if I took the moment of inertia of this whole rectangle and then subtracted out the moment of inertia of these two inner rectangles that aren't there, we come up with the same answer as if I were to look at each of those three rectangles independently.
Are we just ignoring the little fillets in the corners?
Yes, because that's all they're giving us. Is the dimensions of our rectangles. So if that's the case, I'm going to start by saying we have 200 millimeters, right? B, or the width times H. Well, the whole depth is 350 millimeters over 12 minus those two inner ones. Well, I'm going to say it's 191 times 318 cubed over 12. 191, well, that is the total width of each of these. Right, it'd be 200 minus 9 is 191, right? Essentially the full width of the black hatched region. Height of it is 350 minus 32, or 318 cubed over 12. We get a moment of inertia of 202.7 times 10 to the 6th millimeters to the 4th. And that is consistent, or what we would use for both of our points, right, in both of our equations, because the moment of inertia is the same throughout the cross section. So if we figure out now this, we'll draw a line here. We're going to look at point H. Well, the normal stress at point H, as we know, is negative my over I. Well, now we have y and I, so we can just plug everything in, right? The critical thing here being we need to make sure we have consistent units, right? We've got an I that's in millimeters, we have a y that's in millimeters, and we have a moment that's in kilonewton meters, right? So we need to convert that. So we got sigma h equals the moment (155 kilonewton meters). I'm going to change this into newtons per kilonewton. I'm going to change meters into millimeters. Going over my line here, but that's okay. Y is negative 35 millimeters. And our moment of inertia is 202.7 times 10 to the 6th millimeters to the 4th. So we get the negatives cancel. and we get 26.8 megapascals or newtons per millimeter squared. Positive, meaning it's in tension at point H in our cross section. Which makes sense. Positive bending, if this beam was going, I think everyone has some intuition at this point, right? If you have vertical forces sitting on a beam, right, the deflected shape is going to be downward. Strain is going to be downward. It's going to have a positive bending moment in it. Positive bending moment means we're going to have compression in the top of the beam and tension in the bottom of the beam. Well, if H is below the neutral axis or the centroid, then we're going to have tension at point H. Similarly, when we calculate the stresses at point K, I would assume that we're going to get a negative number. Okay, we're going to do this. So if we do stresses at point K, we get negative. I'm going to leave the units out so I can actually fit this in. Now we have 180 kilonewton meters multiplied by 1,000 newtons per kilonewton, 1,000 millimeters per meter, and we have a positive 75 millimeters as our Y, and then we have 202.7 times 10 to the 6th. We end up getting a sigma K equal to negative 66.6, such a bad number, megapascals. Being superstitious, right? This isn't good. Let me just do this. 1. Which intuitively makes sense. Compression in the top of our beam, tension in the bottom. Those are our normal stresses due to the applied loads at those 2 points of interest, okay? We will continue on Monday this example and hopefully start another. Don't forget the homework due today. Don't forget the quiz, okay? 5% of your grade.